Hi everyone, this video is about section 2.4 of our text on relations and equivalences. You see here several bullet points of things that we are to discuss in this section. Out of all of these things, probably the notion of an equivalence relation is the most important thing. So you might remember that given a set S, you can form the Cartesian product S cross S that consists of all ordered pairs of elements of S. Now, a relation is just a subset of the Cartesian product S cross S. So a relation technically is going to be a collection of ordered pairs on S. So if R is a relation on S, we can say that an element A in S is related to B in S if the corresponding ordered pair, A comma B, is in the subset R of S cross S. So oftentimes, instead of writing ordered pairs like this to indicate that two elements of S are related, we're going to write just A, R, B here to indicate that they are related. And if they're not related, as in here, then we write A, R, B with a slash through the R. This idea of a relation might seem foreign to you, but really you've seen relations all over the place before in math. In particular, these symbols, equality, less than, greater than, less than or equal, and greater than or equal, those all define relations on the set of integers, or really on any set of numbers. For instance, let's suppose that capital S is this finite set consisting of the numbers 1, 2, and 3. Then there's a relation on that set determined by less than or equal, and it consists of these three ordered pairs. Why does it consist of those three ordered pairs? Well, 1, 2 should be in this relation because 1 is indeed less than 2. And similarly, 1, 3 because 1 is less than 3. And 2, 3 because 2 is less than 3. But notice that, if we call this relation R, say, 2 is not related to 1 because it's not true that 2 is less than 1. Okay, so in the second bullet, we have another example. So let's let P be the set of all people. And for any specific people, A and B, we'll say that person A is related to person B if A and B are or were brothers. Turns out that R is a relation on P, and in fact, the ordered pair Cain, Abel is in R because Cain and Abel were brothers. Finally, why don't we let W be the set of all web pages? Then we can form a relation L on W where a website A is related to a website B if the website A has a link in it to website B. If X is a finite set and R is a relation on X, then R can be represented by a directed graph. So how does that work? Well, we let all of the elements of X be vertices. So we have these elements of X here that are vertices. Let's say A, B, C, and D. And we draw an edge between the two vertices whenever those vertices are related under R. So for instance, if A is related to C, then we would make sure that in our graph we would draw a directed edge from A and ending at C. Okay, here's an example of a relation that's represented by a directed graph. So here, this relation is the divisibility relation on this finite set X consisting of numbers 2, 3, 4, and 6. Now I want to remind you that A divides B means that A divides evenly into B. So A divides evenly into B. All right, so our set X, again, consists of numbers 2, 3, 4, and 6. And so we draw a graph where the vertices are 2, 3, 4, and 6. And then we draw an edge between any two vertices in the graph whenever one number divides evenly into the other. For instance, if we look at, 2 and 6, for instance, so here's 2 and here's 6, it is indeed true that 2 divides 6. That is, 2 divides evenly into 6. And therefore, there's a directed arrow from 2 to 6. However, 2 does not divide evenly into 3. And so if you look at 2 and 3, there is no directed arrow from 2 to 3. Now, this graph has some loops, like, for instance, from 2 to itself, and that's because 2 does divide evenly into 2, and therefore we get this loop that begins and ends at 2. So when we have a relation and it's represented by a directed graph, sometimes you don't need directed arrows. In fact, just plain edges will suffice for some relations. That will happen exactly when our relation has a symmetry property. That is, when X is related to Y implies Y is related to X and vice versa. So then it suffices to just use the undirected graph corresponding to that relation. So here we have an example of a symmetric relation. Our set X, again, consists of the numbers 2, 3, 4, and 6. But this time, instead of using the divisibility relation, which is not symmetric, we're going to use this new relation R, where we say that A is related to B exactly when A times B is less than 13. Now, A is related to B. That happens exactly when B is related to A. Right? Because A times B is less than 13 exactly when B times A is less than 13. Right? That's because A times B and B times A give the same product. So if one is less than 13, the other will be less than 13. So here, notice that there's an edge joining 2 to itself, and that's because 2 times 2 is 4, which is less than 13. And there's an edge joining 2 to 6, because 2 times 6 and 6 times 2, those are both less than 13. Notice, however, there's no edge from 6 to 4, and that's because 6 times 4 is not less than 13. If we're given a function from a set to itself, that is, suppose we have a function f from x to x, then that function naturally gives rise to a relation R, where A is going to be related to B exactly when B is equal to f of A. So the point is that every function from a set to itself determines a relation on that set. But the converse statement is not true. That is, if you're just handed a relation on a set X, for instance, that relation does not naturally determine a function. Now, why is that? Well, let's take a look at this set X that's given in the example here, 2, 3, 4, 5, 6, 7, and 8. And let's think about the relation on X that's determined by this directed graph, okay? So in particular, we see that 2 is related to 4 because there's a directed edge from 2 to 4. And 2 is related to 8 because there is a directed edge from 2 to 8. Now, that does not determine a function from X to X because, the problem is that the value of our function at 2 is undetermined. We wouldn't know whether it should be 4 or whether it should be 8. And remember that any function must take an input to a single output. But here, our input 2, we don't know whether to send it to 4 or to 8. So the upshot is any function from X to X determines a relation, but the converse is not true. There can be relations on sets that do not determine functions. Arguably, the most important type of relation is something called an equivalence relation. And the idea here is that we want to generalize the notion of ordinary equality, right? So equality plays a very important role in our number systems. Now, what are the sort of the fundamental properties of equality? Well, we know that anything is equal to itself, right? So that's a fundamental property. And we know that if A is equal to B, then B is also equal to A. So equality has a symmetry property, and it's transitive. Like if I know that A is equal to B, and I know that B is equal to C, then that should imply that A is equal to C. So these three properties, which we call the reflexive property, the symmetric property, and the transitive property, those are properties of equality that we want to hold for any equivalence relation, right? So again, a relation R on a set S is an equivalence relation if it's reflexive, if it's symmetric, and if it's transitive. There are many, many examples of equivalence relations. On this slide, we give just a few. Now, as we pointed out on the previous slide, ordinary equality is the classic equivalence relation. It's reflexive, it's symmetric, and it's transitive. In our second bullet point, we're going to let S be the set of all symbols of the form x over y, where x and y are integers and y is not equal to 0. So in other words, S is the set of fractions. And we can define a relation R on the set of fractions as follows. So if we've got two fractions, x over y and z over w, we say that the first x over y is related to the second z over w if x times w equals y times z. So you might recognize this relation as just checking to see whether cross multiplication gives equal values. Okay, so this R is an equivalence relation, and if two fractions are equivalent, then they represent the same number. Now finally, we have this equivalence relation involving functions. So suppose we just have any function f from a set x to a set y. We can define a relation on the domain of our function in the following way. So if we have two elements, a and b, in the domain, we say that a is related to b if the two output values, f of a and f of b, are equal. So this R relation turns out to be an equivalence relation. On this slide, we continue to discuss the last example on the previous slide. So remember here, we have a function f from x to y. And we define a relation on x by a is related to b if the two output values, f of a and f of b, are equal. So we claimed on the previous slide that this relation R is an equivalence relation. And now we're going to prove that that relation is indeed an equivalence relation. So to do that, remember that an equivalence relation has three fundamental properties. First is it's reflexive, then it's symmetric, and third, it's transitive. So reflexive property states that if you take any A in our set, that A is related to A. So let's check that. Well, if you take f of A, that's clearly equal to f of A, and that means that A is related to A under this particular relation. So next we have symmetry. So to verify symmetry, we want to show that if A is related to B, then it's also true that B is related to A. So let's suppose A is related to B. Then by the definition of this relation, that means that f of A is equal to f of b. But ordinary equality is symmetric, and so that means that f of b is equal to f of a, but that's equivalent to saying that b is related to a, and we're done, right? Remember, we started with a being related to b, and we wanted to show that that implies b is related to a. So finally, we have this idea of transitivity. Right, so we take three objects in our set X, and we suppose that A is related to B, and B is related to C, and our object is to show that A is related to C. So if A is related to B, then that means that f of A is equal to f of B. If B is related to C, that means f of B is equal to f of C. But now, ordinary equality is transitive, right? So that means that f of A is equal to f of C. And in other words, A is related to C, which is what we wanted to show. So if we're given an equivalence relation R on a set S, we can form what are called equivalence classes on S. So what we do to do that is we first start with, say, a specific element of S. And then we ask ourselves, what is the collection of objects in S that are equivalent to the specific object in question, namely X? So we go out, we search for all of the things in S that are equivalent to X. And that object, this R sub X, is the equivalence class under R containing the element X. So we can do that for a variety of specific elements of S. And if we do that, what that does is it splits S into a collection of these equivalence classes. Now, one thing that's interesting about equivalence classes, let's suppose we have equivalence class R sub A and R sub B. Right, so R sub A is going to be all the stuff in S that's equivalent to A. R sub B is going to be all the stuff in S that's equivalent to B. Exactly one of two things can happen. Either these are equal, or they have nothing in common whatsoever. that is the intersection of RA and RB, is the empty set. So these equivalence classes, if you put them all together, they will give you the entire set S. And furthermore, they form what's called a partition of our set, meaning that together they form all of S, and pairwise their intersections are empty. Here and over the next several slides, we're going to be talking about a particularly important equivalence relation called the modulo n relation. So typically what we do is we start with an n, which is actually going to be some positive integer. And we say that two integers a and b are related modulo n, or equivalent modulo n, exactly when their difference, a minus b, is divisible by n. Okay? So a is going to be equivalent to b modulo n exactly when n divides evenly into the difference a minus b. So for example, we have this giant list of numbers here, right? 1, 4, 7, 10, 13, etc. Any two numbers in that list are equivalent modulo 3. So why should that be true? Well, so we assert, for instance, that 7 is equivalent to 13 modulo 3 because if I take 7 minus 13, that number is divisible by 6. Right? 7 minus 13 is minus 6, and that's divisible by 3. Okay? Okay, so one thing to notice is that two numbers, a and b, are equivalent mod n exactly as we said above, when n divides the difference, a minus b. That means that a minus b is some multiple of n, and that means that we could express a as b plus some multiple of n. So what that means is that if you start with any number b, your favorite number, and you add on any multiple of n, you will wind up with another number a that is equivalent to b modulo n. Okay, here we're going to verify that the mod n relation is an equivalence relation. So first, we need to show that it's reflexive. Right? So a is definitely equivalent to a mod n. Because n divides evenly into a minus a, right? N divides evenly into 0. Right, so just to check that, remember here that 0 equals n times 0, right? So that says that n divides evenly into 0. Okay, so this is a reflexive relation, and now we need to check that it's symmetric. So let's suppose two numbers are equivalent, mod n. Suppose a is equivalent to b, mod n. Then that says that n divides evenly into a minus b. And so if n divides evenly into a minus b, it should divide evenly into its negative, namely b minus a. And from there, we can conclude that b is congruent or equivalent to a mod n. Remember, that's what we wanted to show. To show symmetry, you start by supposing a is related to b, and you do some things to show that b is related to a. Okay, so finally we have this business of transitivity. Okay, so let's suppose we have a congruent to b mod n and b congruent to c mod n. That implies that a minus b is divisible by n, meaning that a minus b is some multiple of n. And likewise, b minus c is some multiple of n. But now if you add these two expressions, if you add a minus b to b minus c, you get a minus c. The b's cancel. And you get n times k plus l. So that means that a minus c is also a multiple of n, which means that n divides evenly into a minus c. And that tells us that a is congruent to c mod n. And that finishes the proof. Remember, for transitivity, we start by assuming a is related to b and b is related to c, and we want to show that a is related to c. Here we investigate the equivalence classes of the mod n relation. So first, a little bit of notation. So we're going to let z slash n, that is going to be equal to the equivalence classes of the mod n relation. And we're going to let, if we put a number inside square brackets, that's going to be the equivalence class containing the number a. Okay, so what we're going to do is a little example here. We're going to find the equivalence classes, or what are the equivalence classes modulo 6. In other words, well, we'll just say it like that. What are the equivalence classes? Modulo 6. Okay, so let's see if we can figure that out. So whatever they are, remember what we said a little bit earlier about equivalence classes. They should all be disjoint sets, meaning that distinct ones have no overlap whatsoever. And taken together, they should give the entire set of integers z. Okay, well, let's start with 0, the equivalence class containing 0. So those are going to be all of the numbers that differ from 0 by some multiple of 6. So if we write those down, well, certainly it will include 0, and it includes 6 and 12 and 18 and so on and so forth. But it will also include -6 and -12. Right? So it's all of these integers that differ from 0 by a multiple of 6. Now we could just as easily have written this. This is also the equivalence class that contains the number 6. But here, we're going to choose 0 to be sort of our team captain here, sort of our representative of this equivalence class. So now what about 1? So the number 1, that's certainly going to, the class is going to include 1, and it's going to include all numbers that differ from 1 by some multiple of 6. So like 7, 13, -5, -11, and so on and so forth. So again, this could be represented by, this is also the equivalence class containing, say, 13. But here we choose 1 to be our team captain. And then we keep going. So 2, for instance, includes 2 and all of the numbers that differ from 2 by a multiple of 6. So 3, so we keep going on our way here. Equivalence class containing 4. Well, it has 4, and then it has all of the numbers that differ from 4 by a multiple of 6. So that would be 10, 16. And then also -2 and -8, and so on and so forth through negative numbers. And then we have 5. Now we could keep going. Let's suppose we wrote down 6. Why would we want to stop right here after the equivalence class containing 5? Well, if we write down the equivalence class containing 6, well, that's exactly the equivalence class containing 0. Right? So we don't want to repeat these, right? We just want to write down each one only once. And notice that if you take the equivalence class containing 0, the equivalence class containing 1, down through the equivalence class containing 5, and you look at the union of all of those sets, you'll get exactly the set of integers with no overlap. So that's exactly what we wanted to have happen. So this is telling us that Z mod 6, that is the equivalence classes of the mod 6 relation are 0, 1, 2, 3, 4, and 5. Now we can form an arithmetic using these equivalence classes mod n. So if I take two equivalence classes represented by A and B, respectively, I can sort of add these two equivalence classes together just by adding the representatives A and B and then considering the equivalence class that contains the sum A plus B. Same for multiplying two equivalence classes. All I can do is just multiply the two representatives A and B, I get a number, and then I look at the equivalence class that contains that number. So down below here we have this example, like in Z12, if I want to add equivalence class containing 6 to the equivalence class containing 8, well, that's the equivalence class containing 14. But 14 and 2 differ by a multiple of 12. And so we could just as easily say that this is the equivalence class, the result is the equivalence class containing the number 2. Okay, a while ago we computed the equivalence classes modulo 6. You might remember they were represented by the numbers 0, 1, 2, 3, 4, and 5. Now we can use the addition and multiplication that we talked about on the previous slide to make addition and multiplication tables for these equivalence classes modulo 6. So here, for instance, if we take 2 plus 5, what we're asking is, well, okay, what's the equivalence class that contains the sum 2 plus 5? So that would be the equivalence class modulo 6 containing the number 7. Well, that equivalence class also contains the number 1, which is sort of our team captain. And so 1 is the result of that sum. Likewise, if I want to take 5 times 4 in this arithmetic, the product 5 times 4 is 20. So I'm looking at the equivalence class modulo 6 that contains the number 20. So 20 differs from 2 by a multiple of 6. And 2 is sort of our team captain here. So the result of the product, 5 times 4, is equal to 2.